Once we're dealing with individual measurements, we may need to use more than one uncertain value and combine them, and this is where propagation of uncertainty comes in. There are lots of rules for propagating uncertainty depending on what kind of math we're doing, and the quantitative analysis book covers all of them, but we're just going to stick with the kinds of math that we are going to most likely do in chemistry. So the math that we are likely to do is going to be addition and subtraction. We do this kind of thing all the time. And a little bit of multiplication and division. And then we do occasionally use logs. And so we're going to need to figure out how to do those, like when we calculate pH. So we're going to start with addition and subtraction rules. All right, so let's imagine a scenario where we have propagated, oh, and I should put a little note here, this is for random uncertainty specifically. Okay, so let's imagine a place where we have measured several different masses using a mass balance. And maybe these are solid reagents that we then need to add together. So our first mass is 2.35, and let's imagine that our mass balance is certain to 0.02 grams. And our next mass is 6.91, plus or minus 0.02 grams. And then our third mass is 4.77. Okay, so when we add up the total mass here, we will just add these three masses together, and that one will give us 14.03. And we can use our significant digit rules to see that in addition we need to keep 2 decimal places, which makes a lot of sense. But if we think about our 3 uncertain values here, these are all random uncertainty, and we know that they could be positive, but they also could be negative. And so it doesn't really make sense for us to just add all 3 of these and get plus or minus 0.06. Probably that would be an overestimate of the amount of uncertainty. So instead what we're going to do is we're going to calculate using sort of a square root of the squares process here. So if each one of these uncertainties, I'm going to label these E1, E2, and E3, we're going to take each of those and we're going to square them individually and then add them together, and that way we get rid of any negatives. We're going to add the squares and then take the square root, and that's going to be our total uncertainty. And this helps to kind of adjust for the uncertainties and take into consideration that our uncertainty is increased since we have 3 measurements, but that probably it's not as much as 0.06. So let's go ahead and calculate this. If you want, you can pause the video and then do it yourself. We're just going to plug in these 0.02s. Oops, not 0.002. So if you do the math here, you should get 0.03 grams for the uncertainty for this total. So we would report our total value for this mass as 14.03 plus or minus 0.03 grams. Right? So that's addition and subtraction rules. And if you have more than 3 values that you're adding up, then you just add as many as you have underneath this square root sign before you take the square root. Okay, so if we're doing multiplication and division, our process is going to be pretty similar, but we do have one additional factor to consider. And I'm going to show you an example that illustrates this problem. All right, so let's think about a situation where we would use multiplication or division. Probably one of the most common ways is for us to be calculating the density of something. Density is defined as mass over volume. And so that's a place where we are doing division. So let's imagine that we have a rock, and we're going to use volume displacement to figure out what the density is. So first we weigh its mass on a mass balance, and let's say that it comes out to 18.482, and this is a mass balance with 0.002 uncertainty on it. And now we use volume displacement, and so we go ahead and measure the amount of space that this rock takes up, and we're using probably a graduated cylinder, so its uncertainty is not quite as precise as with our mass balance. So let's see that our uncertainty for this is 0.05 milliliters, and 8.60 is the volume that we actually read. So we're going to go ahead and calculate the density again. So go ahead and pause the video and calculate this. Plug in your mass over your volume. So if you do that, we'll have 18.482 grams over 8.60 milliliters. And we will get 2.15 grams per milliliter. But when we try to use the same equation that we did before, right? We would have E1 squared plus E2 squared. Do you see the problem already, right? This would be 0.002 grams squared, and this would be 0.05 milliliters squared. And I can't add grams squared and milliliters squared. That just does not work. They have different units. I cannot combine them that way. So if we cast our mind back to talking about uncertainty, we actually have to do something that's slightly different here. So we're going to calculate instead the relative uncertainty or the percent relative uncertainty, and either one is okay. Most people prefer to do the percent relative uncertainty just because it's easier to keep track of the fact that you don't have the absolute uncertainty. So we'll go ahead and do that here. So we're going to calculate the percent relative uncertainty. So why don't you pause the video for just a second and calculate the percent relative uncertainties for the mass and the volume. Okay, so those percent relative uncertainties should look like this. Notice that as soon as I do the relative uncertainties, I'm dividing out my units. And now this allows me to combine my percent relative uncertainties with no problem. Oop, I lost these plus or minuses, but I'll put them back. So because the 0.01% is quite a bit smaller, it turns out to not affect our percent relative uncertainty for the total answer. This is normal when you have two uncertainties that you're combining or multiple uncertainties and one of them is much larger than the other. That is the one that's going to dominate what the total uncertainty is for your answer. Okay, so 0.6% is not something that I know sort of how to convert in my head, so I'm going to go ahead and calculate the absolute uncertainty as well for my final answer. I had 2.15 grams per milliliter for my final answer. And if I want to get from the percent relative uncertainty back to the absolute uncertainty, this is something that students often find a little bit confusing. And so what I'm going to remind you is that when we calculate the percent relative uncertainty, we do this by taking the absolute uncertainty and dividing it by the number, like the density, and then we multiply it by 100%. So if we want to go backwards to the absolute uncertainty, we just do this in reverse. We multiply by that number and then we divide by the 100. So let's go ahead and do it. We have this number, which is the density. We're going to multiply by the percent relative uncertainty, 0.06%, and we're going to divide out the 100%. So when we do this, we should get plus or minus 0.01 gram per milliliter for our absolute uncertainty. And depending on the question, they may ask you for the absolute uncertainty, they may ask you for the percent relative uncertainty. So just pay attention to whatever question is asking and make sure that you're doing that. And as I just mentioned, if you forget how to go from percent relative to absolute, just write out the process that you would do and then just undo it. Okay, so there's a lot of other math, as I mentioned, in the quantitative analysis chapter, but the other ones that we really care about have to do with pH. So if we think about, if we calculate pH, this is minus log of H plus, and then sometimes we go the other direction. So we'll calculate the molarity by going 10 to the minus pH to undo that log base 10. So that implies that we really should pay attention to the logs, and then we should pay attention to 10 to the exponent. So let's go ahead and see how to do those examples. Right, so for log base 10, our generic format for that is y is equal to log of x. And our generic way of calculating the uncertainty of our answer is to take 1 over natural log of 10. This is natural log, not log base 10. And then we're taking the uncertainty of that x value divided by it. So this is really just the relative uncertainty of whatever the x number is. So let's go ahead and look at an example. An example here for us would be if we have a concentration, let's say we have 0.009345 molar. We've done a very careful titration series and we've been able to calculate our uncertainty here, which is 5 times 10 to the minus 6 molarity. So that's the same thing as 0.000005 molar. Okay, so we have carefully calculated this molarity. We want to carefully calculate the pH with just as much precision. So let's identify what the pieces are. So here's my y equals log of x. My equation to calculate the pH is minus log of H3O plus. The minus sign doesn't do anything to how we calculate the uncertainty. So that means that my x here is my concentration. So this is equal to x, and that means this is equal to E sub x. So once we identify these parts, then it's pretty easy for us to calculate the uncertainty. So the uncertainty of the pH, that would be y, will be equal to 1 over the natural log of 10, 5 times 10 to the minus 6 molar, our uncertainty, divided by our concentration, 0.009345 molar. So if you calculate that, then we will get 2 times 10 to the minus 4 as the uncertainty in our pH. We also haven't calculated our pH yet, so let's go ahead and do that. Now is a good time for you to pause the video before I put the answer down. Hopefully you have also calculated that we have 2.0294 as our pH. So our uncertainty would also look like 0.0002. And recall that pH is a unitless number, and so this matches up really well with the fact that we have calculated a relative uncertainty here and canceled out the molarity units. Of course, most of our pH probes are not this precise, but that's okay. So if we want to go the other way around, we have pHs and we want to go to molarity, then we're going to use a 10 to the power of x rule. So let's have an example here. Let's say our pH is 3.142 plus or minus 0.001. And now we want to go and figure out what the concentration plus its molarity is. So our generic format here is y is equal to 10 to the x, and our generic format for the uncertainty is actually in the form of the relative uncertainty for y is equal to natural log of 10 times e to the x. And if you are paying attention, this is kind of the reverse of what we just had right up here for logarithms. So that's kind of handy. It means we don't really have a separate rule, we just have to undo the thing that we just did. Okay, so if we look at the pH, and I just had written up there how we calculate the pH. We calculate our concentration as 10 to the minus pH. And so looking at our generic rule here, that means that y is equal to our concentration of H+, and that x is the pH, and the negative sign does not change our process, so we don't have to worry about it. So our relative concentrations uncertainty divided by our H+ is equal to natural log of 10 times the uncertainty of the pH, so that's plus or minus 0.001. We also need to calculate the H+ right here, so let's go ahead and do that. 10 to the minus 3.142. Pause the video here and calculate that. Hopefully, when you calculated that, you should get 7.21 times 10 to the minus 4 molar. Now stop for a second and ask yourself why I put down 3 significant digits here. Hopefully you remembered that we have 3 decimal places on the pH, and this 3 is a placeholder. And this is why these 3 significant digits match each other. So when we plug in 7.21 over here, actually what I'm going to do is I'm going to calculate the uncertainty for the H+. So I'm just going to go ahead and multiply this guy by the right-hand side. So that looks like 7.21 times 10 to the minus 4 molar multiplied by natural log of 10 and plus or minus 0.001. So pause the video, take a second, plug that into your calculator, and you should get 1 times 10 to the minus 6 molar, or since this is in 10 to the minus 4 molars, we should get 7.21 plus or minus 0.01 times 10 to the minus 6 molar. And this format implies that both the 7.21 and the 0.01 are multiplied by the 10 to the minus 6. So there's sort of an invisible parentheses here applying these to both of them. Okay. So I'm going to have a couple of example problems for you to work, or practice problems for you to work in the assignment at the end of this section. And I want to just remind you that these are 3/4 different kinds of ways to propagate uncertainty. There are different ways depending on other math. If you run into some other math, you can just look them up in this section, which is 3.4 in the quantitative analysis book. So all of this propagation has been for random uncertainty. And most of the time we try and just correct for systematic uncertainty. But in situations where we can't, and there are a couple, then we have to be able to deal with it as well. So you may or may not know this, but one of the places where systematic uncertainty comes in that we really can't avoid is for molecular weights or atomic weights. And this is because atomic weights are averages, which you probably remember from Gen Chem, that we calculate the average atomic weight based on the natural abundance of each element. The isotopic abundance of each element varies depending on where you are on the planet. And this can actually be pretty localized. So even areas that are pretty close to each other can have slight differences in isotopic abundances. And so if you're calculating the average atomic weight, it depends on the isotopic abundances. And since those vary, there's some systematic uncertainty that comes in depending on where you are. So this is actually a pretty interesting area of analytical chemistry. You can do trace analysis for authentication. And it's used for authenticating agricultural products like wines. You may or may not know that wines such as Champagne and Riesling, you can only use the name Champagne or Riesling if those wines are actually from, respectively, the Champagne region of France or the Riesling area of Germany. So it's kind of important for branding for people to be able to be sure that these wines really come from that area. It's a big industry. So long story short, since there's not a uniform distribution of isotopes everywhere around the world, we have this unavoidable systematic error in atomic masses. And so we need to be able to account for it when we are calculating atomic weights and molecular weights. So as a quick review here, I want you to try to remember how to calculate the average atomic mass of an element. So for example, chlorine is a good one. It doesn't have too many different isotopes. And so go ahead and review that. So calculate the atomic mass using the isotopic abundances that are available and verify that it matches the mass on the periodic table. I've added a review section if you don't remember how to do this, and I will note that a good place to find these is Web Elements. Okay, so hopefully you're back from having done that practice. So when we want to propagate uncertainty, we're going to use some of the same tools for systematic error that we've already used, and also some slightly different ones. So let's look at something like a heteronuclear diatomic molecule, like, I was just going to do sodium chloride, not silver chloride. Okay, so when we calculate it for a heteronuclear, hetero means different, nuclear means atom. Diatomic means 2 atoms. So these are different. There's 2 of them. That makes this a heteronuclear diatomic, in case you haven't heard that term before. So for a heteronuclear diatomic where we just have 1 atom each of 2 different elements, our process looks just like the one that we did for random error. So if we go to our periodic table, this is the one that's attached to the Moodle, and let's pop over to it for just a second and get the atomic masses for sodium and chloride. So here's our periodic table. It's one that I scanned from the front of the quantitative analysis book. It's not in the PDF, which is why I scanned it separately. So here is sodium. And so let's go ahead and write that down. 22.989770 plus or minus 2. And chlorine is on the second page, 35.453 plus or minus 2. So one thing that I want to note is that when this says plus or minus 2, it doesn't mean like plus or minus 2. What it means is plus or minus 2 in the last certain digit. So we would formally write the uncertainty as plus or minus 0, 0, 0, 0, 0, 2 atomic mass units. And for chlorine, 35.453 or plus or minus 0.002. All right, so when we calculate the molecular weight, we're just adding up these two as normal, getting 58.443 atomic mass units, keeping 3 significant digits because we're using addition rules. And then our total uncertainty would be the square root of E1 squared plus E2, just like for random uncertainty. Here's E1, here's E2. And so if you plug those in, you should get plus or minus 0.002 atomic mass units for your final uncertainty. All right, so this works just fine for any heteronuclear diatomic. However, if we have a polyatomic, like, for example, benzene, then we have a slightly different situation. If we look up our atomic masses, so go ahead and pause the video and look those up for carbon and hydrogen. When we calculate the molecular weight, we know that we have 6 carbons and 6 hydrogens. And when we calculate the molecular weight, we are used to having to calculate or multiply by 6 for the atomic masses. So if we do that, we would add them up and get 78.1118 atomic mass units. But when we calculate the uncertainty for this number, we need to multiply our uncertainties by 6 also, because we have 6 carbons and 6 hydrogens. So with random uncertainty, we wouldn't multiply by 6, but because we know that this is a systematic uncertainty, that the systematic error affects every single one of those carbon atoms and those hydrogen atoms, that is why we multiply that uncertainty by 6. So that means that the carbon's uncertainty is going to be 6 times plus or minus 0.008, and the hydrogen's uncertainty is 6 times plus or minus 0.0007 atomic mass units. Or, in other words, 0.0048. I'm going to leave those extra digits in for right now. And guess this one is a little small, so we'll just say 4.2 times 10 to the minus 4 atomic mass units. So when we calculate the total uncertainty, we're going to use these modified amounts. So go ahead and pause the video and calculate this. Hopefully you got plus or minus 0.0048 atomic mass units. So now we actually need to talk about that last digit of the uncertainty. Because in uncertainty, there's very few cases where we're going to keep two significant digits for that uncertainty. Instead, we're going to round, or we're going to indicate that that uncertainty is uncertain in some other way. So if we look at this number, 78.1118 atomic mass units, plus or minus 0.0048 atomic mass units. Notice that the last certain digit now, based on the uncertainty, really needs to be in the thousandths place, not the 10,000ths place. So we have two options for rewriting this. We can either write 78.112 plus or minus 0.005 atomic mass units. Or we can write 78.111 and then subscript 8 plus or minus 0.004 subscript 8 atomic mass units. And either one of these is okay. Typically the convention is for us to either round all the numbers or use subscripts on all the numbers, not mix and match. So we've just gone through how to propagate uncertainty for 3 different cases of random error and also for systematic error. And now you are ready to do assignment 2. So at the end of this video, please go to chapter 3, the problems at the end of the chapter, and try problems 3.6, 3.15, 3.17 parts B and C only, and 3.18.